if this, okay. I think we're streaming. Yes. Well, it says we're streaming. So, welcome, Katherine, to our group meeting. Everybody, this is Katherine Van Kirk. She did her, am I right in saying you did your undergrad at Stanford? Is that right? Mm-hmm. And you're a graduate student now in Misha Lukin's group at Harvard. How long have you been a graduate student?
Yeah, so I am in my third year.
Third year.
But actually, when I was at Stanford, I studied engineering, and it was engineering physics, but it definitely had more of an engineering.
Engineering physics?
So
I have a degree in engineering physics. How about that?
Oh, really?
Yep.
That's cool.
Yeah.
Wait, also at Stanford?
No. I was at Queen's University in Canada.
Oh, so, that's awesome.
Yep.
But I have been out of undergrad for a little while because after Stanford, I went to Cambridge where I studied math, which helped me a lot before coming to Harvard and starting doing theory with Misha.
I see. So let's see. So today you're going to tell us about, I had this all set up. So today you're going to tell us about hardware efficient learning of quantum many-body states. And Gaurav, I guess, went to your talk at the March meeting and kept talking about it afterwards for several days. So I thought we should definitely have you come to our group meeting and tell us about it. So let me let you take it away.
Yeah, thank you for inviting me. I'm going to share my screen. And as I do that, I love the fact that it's like an intimate group, and also along those lines, I would love if you guys interrupt me and ask me lots of questions, because it's more fun for me, and also I feel like you take more away from it. And I know that it's hard sometimes on Zoom to facilitate that, but as much as you guys can, I really welcome it, and I want to be approachable.
Sounds good.
Yeah. Okay, so Michael gave me a lovely introduction and mentioned what I'm going to be talking about, but basically I'm going to discuss work that I did that we published or put on the archive in December. And I put the archive link here, as you can see. And you guys can see my slides, right?
We can see your slides fine, yep.
Okay, amazing. And so I highly recommend you to follow along, or of course, if you have more questions after the fact, you can use this link and go look it up. And I mentioned a few at the very end, ideas that I have for further work that actually I've been pursuing, but I'm also happy to answer questions on that, and I have a few backup slides if you're interested in hearing more. Okay, so I'm going to be talking to you today about work that I did with Jordan, Robert, and Misha, and I adore them all. And the main problem that we're trying to tackle with our work is how do we learn the properties of large quantum systems. And these properties are typically things that are really complicated. And it might be like security, or some complicated order parameter, or some fidelity with a really intricately constructed state. And it turns out that actually doing this is really, really hard. And one of the reasons why this is really hard is because oftentimes on your quantum simulator, you cannot actually directly measure this property of interest. For example, if you have some Wilson observable that's fattened, that's going to be really tricky to actually probe. Or even sometimes you might have seen that people actually can probe the purity, but you can only really do it on small system sizes. And the way that people have done this in the past, and it's okay, it's you haven't seen these sorts of things, but basically the way that people do things is they create two copies of the same system. In both of these cases, they consider a 1D chain, and then they interfere them with a sort of beam splitter style measurement. And if that doesn't mean anything to you, you can consider a swap case, and then they measure and they can extract the purity from that data. And here we have two examples of this, one on a Bose-Einstein condensate, another one on a Rydberg atom array, and kind of fun, both of them happen here at Harvard. And doing this obviously on small system sizes is practical, but when you actually scale this up, this can be really challenging, both because, say, if you're doing this in 2D, some systems can't interfere two copies in 2D, and also if you have a really large system, you might not be able to make two copies of the large system that you're preparing just due to experimental limitations. So what people do instead is they often use randomized measurement. And this right here gray is a randomized measurement, and it has kind of three separate steps. The first is you prepare your state, that's what's happening in green. Then you perform some unitary, and then you measure all the qubits in the Z basis, and you get out some computational basis state, which here I've indicated as D. And crucially, the thing that I want to mention before I go into more about how this works is that the unitaries that you're sampling are from some ensemble, which here I've denoted as this like script curly D. And that ensemble is something that people like
Katherine?
when they theorize. So yeah.
Katherine, did you say the measurements all happen in Z, or is that what I heard?
Yeah, so you measure all of your qubits in the Z basis, but effectively, because you're doing like a unitary rotation before measuring, you're not measuring in the Z basis, but like you're measuring in whatever Z dagger like Z is.
And that randomized thing is the whatever happens from the rotation.
Exactly.
Okay.
And so you can imagine that like if you have a larger set of unitaries that you're sampling from when you do these, then you have like a larger set of randomized measurements that you're sampling from.
Thank you.
Amazing. Yeah. Okay, so this is just the building block. So what you do when you actually do these sorts of protocols is you perform many of these randomized measurements, and you, as a result of doing that, collect a bunch of data where each shot gives you kind of two pieces of information. One is the unitary that you applied, and the other is the actual computational basis state that you got at the output. And so you have a bunch of data after you've done this, and then you use that data to actually extract out the property that you're interested in learning. And this, for example, could be some complicated work parameter O. So at a high level in the randomized measurement paradigm, you do a bunch of randomized measurements, you post-process, you learn your property of interest, and thus you have achieved your goal. And the way that people typically talk about this is that you can not just learn maybe one property of interest, but learn many. And kind of a reason why these protocols have been so interesting is because of the fact that you can learn many properties by doing all these randomized measurements. And in fact, people have shown rigorously that you can learn exponentially many properties of your system using only polynomially many measurements, which is super cool and really demonstrates the power of what's going on here. So I'm going to now just give you a little bit of background on what previous protocols have looked like to just get you situated and make you experts in the field. First, I want to tell you about some protocols that came out first from groups at Innsbruck. And they have actually done experiments utilizing these protocols, which are super cool, and I highly recommend you read these papers if you haven't already. Basically, they have applied a bunch of randomized measurements, like I mentioned, but what's interesting is that they say, like, okay, we want to learn, say, the purity. As you can see, that's something that they're plotting here. And then they come up with this, like, at the surface, like, very complicated looking expression for how to take the measurements and actually backtrack out the purity. And they have these really beautiful mathematical derivations for why this works. And they do this for a bunch of different properties. And the experiments that have come like after the fact of all the theory coming out have been very successful. For example, this one was in science, and was about many-body localization, and really kind of like set the scene for like the randomized measurement toolbox. Then following this,
can I ask a quick question? So, how many shots did they need to take to get a good estimate?
Yeah, so for this particular experiment, I don't know, for the figure that I'm showing, I don't actually know how many shots they took. But one of the things that was interesting is that the classical shadows paper compared their work to these original protocols, and it seems like the number of measurements kind of is on the same footing as classical shadows.
Okay.
Like the classical shadows paper from Robert, Richard, and John. Yeah, which is interesting. And also, actually, all of those authors, these authors from these like Innsbruck protocols and the classical shadows folks came together and put out a paper called the Randomized Measurement Toolbox, which kind of like shows a connection between these two different, like at first, different looking protocols.
I see.
So the sample complexity is still exponential in the subsystem size.
Yeah, for learning purity for both of these cases. So for classical shadows, for those of you guys who don't know, it came after Aronson came up with this idea of using, instead of having like a full reconstruction of the density matrix to learn your property of interest, you could construct like a classical shadow. And he theorized about this and showed that you can actually still learn like really interesting properties of your system by only learning this quote unquote shadow. And then the paper that I just mentioned by Robert, Richard, and John came out after that. And as a result of this work, this has spurred tons and tons and tons of papers that are all really great, one of which actually came from your group, and has like really kind of opened the door to people to study this randomized measurement paradigm. And I guess before I move on, so kind of like one high level thing that I want to say and have like you guys take away from this is that the like name of the game in these protocols is how do I learn my property of interest with as few measurements as possible. So all the people are trying to do here is be as efficient as possible while learning obviously what you want to know to within whatever position you're interested in.
Yeah. For reference, in our paper, I don't think we were, let's see, we did a direct calculation of purity kind of like this, and we needed 100,000 shots per point.
Really, like
you remember that, Robert?
Yeah, it went noisy really fast.
So that was a lot of shots, right? So we weren't using it as effectively as we could have been.
Well, maybe I should say then to clarify, like some experimentally motivated work on classical shadows looks at that. And also I should say, like as someone in Nisha's group, one of the like beauty of being in his group is that we have amazing experiments, and so a lot of like the work that we do is thinking about like how do we tailor protocols that exist in theory land and make them more efficient so that our experiments can actually utilize them as efficiently as possible. Okay, so that actually is a great segue into what I wanted to move into next, which is a permeating ideology in this field of randomized measurements. And this ideology is measure first and ask questions later. And this appears in introductions for many, 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 many papers in this field. And so as a result, we should talk about this. And like basically, this ideology is saying that randomized measurements give you access to learn anything you want to learn. And so if you have some experiment that has the capacity to do randomized measurements, then you should just take a bunch of data, and then later on, for whatever it is you want to learn, you can just then backtrack out those quantities from the data that you've taken, which is where this idea of measure first, ask questions later comes from. But as young, smart people, we should ask, is this always the case? And I have a couple things to say about this. First, in most experiments, you know what you want to learn before you measure. Like, for example, if you're preparing some interesting like topological spin liquid in your quantum simulator, you know that there are certain observables that you are wanting to learn and certain things that you're not actually interested in. And as a result, if these randomized measurements give you access to like any operator you could possibly be interested in, then by giving yourself access to all of these things, you're being kind of wasteful, because the measurements that you're taking that give you access to all these other properties could instead be used to target the one thing that you actually really do want to learn, or the like set of things that you actually really do want to learn. So this kind of ideology is really interesting and maybe in some settings really cool, but for experiments, it actually might be a little bit wasteful. So instead, maybe a better question to ask in the context of this randomized measurement toolbox is, how do we tailor randomized measurements to the observables that we're interested in learning? And that is going to be what I'm talking to you guys about today. So this talk is going to break down into 3 different sections. First, I'm going to talk about if you have some quantum simulator with some set of controls, how do you frame a randomized measurement protocol in terms of these controls? And this is really important and hasn't actually been done before. It's just kind of, further deepening the connection between these kind of theorized protocols and what you can do on a given device. And then next, I'm going to talk about, again, like how do you actually tailor this randomized measurement protocol to learning tasks. And then finally, I'm going to show you how our methods work in practice. And specifically, I'll show you how we efficiently estimate the energy density of U1 lattice gauge theory. And it's very, very cool and really shows the power of what we're doing here. So hopefully you understand everything, and then when you get to that point, you will be mind blown. Okay, so let's begin. Again, the goal here is to talk about this randomized measurement protocol for any experimental controls. And this is really important because there are lots of different types of quantum simulators, right? You might have a Rydberg atom array, you might have a superconducting device or a photonic device. And of course, all of these different controls are going to have different capacities, and or even two separate Rydberg atom arrays might have different abilities to control their qubits. And so a really important question to ask is, given certain experimental controls, what can we learn? And I'm going to formalize this, but first I think that it's most illustrative to start with an example. So I'll start with this example, which is global SU2 on 2 qubits. And literally all we're doing here is, again, we're returning to this randomized measurement circuit where you prepare your state, and then you sample some unitary from SU2, and you apply that unitary to every single qubit in your system. For here, we're just considering 2 qubits because we want to keep it simple, for an example. And you might imagine, because there's no entanglement between the 2 qubits, you're not, with this type of control, able to actually learn everything that you would be interested in learning about your quantum system. Specifically, there are some operators that you can learn and some operators that you can't learn. And it might not be obvious immediately looking at this, why we separate them like this, but if you've read Aram Harrow's Search of the Symmetric Subspace, you might have a little bit of intuition. Basically, if you look at the things you can learn, they're all permutation symmetric. So we have 2 qubits here, so the permutations we're considering are identity and swap. And you can see that if you apply either of those permutations on any of these operators, then the operator doesn't change. And you can see that, this might make sense for this particular choice of unitary, because if you look at the unitaries, you're applying the same unitary on every site. So if you permute the unitaries, you're not actually changing the measurement you're doing. And so a kind of high-level intuition you can take away from this is that the measurements that you do are going to affect what you can learn. And the structure of those is going to affect the structure of the observables you can learn. And in our paper, we formalize this, and we develop some language to talk about these things. Specifically, we say that the things that you can learn are visible observables, and the things that you can't learn are invisible observables. And now, just to generalize this and be super concrete, if you have a quantum simulator, there's a certain set of unitaries that you can apply to do your randomized measurements based on the controls available. And this set is this curly script B. And for a really powerful quantum simulator, you might be able to learn everything in any observable you're interested in. But for one that's less powerful, you might only be able to learn some. And so when you choose a quantum simulator, you inherently get this set of unitaries you can apply, and that bipartitions the operator space into things you can learn and things you can't learn, the visible space and the invisible space. And what we show is we have a theorem, which I can talk about how we prove it, is that you can learn exponentially many properties with only polynomially many measurements, as long as the observables you're learning live in the visible space.
So I guess there's also a efficiency. I guess there's, if you think of visible space, there's going to be some regions of that visible space where you can efficiently learn things, even if you're far away from the invisible space border, right?
Yeah. Yeah, you could further imagine kind of slicing up the visible space into sections where some parts of the visible space are going to be really easy to learn and other parts are going to be really hard to learn. Yeah, exactly. Yeah, that's great intuition. And you're foreshadowing something I'm going to talk about. Yeah. Okay, so
question. So this is an improvement over classical shadows, because in classical shadows you predict properties for system of size m with log n measurements, but here it's the number of observables is m instead of the system size. How?
Yeah. So this statement is actually it's very similar to what they show in classical shadows, right? They also show in classical shadows that you can learn exponential many properties with only polynomially many measurements. But the key difference is that in classical shadows, they define that for unitaries that are tomographically complete, i.e. they always start their setup with the case where you the visible space is the entire operator space. And so they never allow for any sorts of control that are more limited, if you will. And so this, what I'm saying here, so there's two pieces when you think about sample complexity. There is, of course, this thing about you can learn exponentially many properties with only polynomially many measurements. And so that's one piece of the statement. And then there's a second piece of the statement, which sort of Michael was alluding to, which is there are some things in the visible space that are going to be more difficult to learn than other pieces. And for the ones that are more difficult to learn, you might say have a sample complexity that scales exponentially with the system size. For example, in the random Pauli space in the original classical shadows paper, if you have an n local observable, it scales exponentially in n.
So there's some benefit to constructing an approach where you have this invisible space. Is that what you're suggesting? Because it gives it restricts things, and therefore other things become a lot more easy to measure.
That's exactly where I'm going to go. Yeah, exactly. And so right now we're just talking about if you have a given quantum simulator, then that only has a certain type of control, then there's inherently an invisible space because of the fact that you can only measure certain things. But later you can change your control such that you choose only certain things to be visible, and then that's going to be a lot more efficient.
Cool.
Yeah.
So sorry, another question. So if you perform these single qubit measurements, right? Then then it's easy to estimate the local observables as compared to bigger observables, longer Pauli strings. So in this case, right, the level of difficulty for estimating these observables is not necessarily their locality, right? Does that make sense?
Yeah. So the difficulty in learning the observable will depend on how tailored the unitaries that you're applying in your randomized measurements are to those observables. So in the case of the randomized, the random Pauli string, it's really easy for you to learn local observables because the random Pauli strings are more likely to overlap with local observables than some specific long Pauli string across your entire system. You're only going to actually be probing that quantity very, very rarely.
Yeah. But in this case, right, it's not necessarily related to locality, right? It might be easy to right. It might be easy to estimate a long Pauli observable compared to a short because you are applying non-local unitaries. This is not
it just depends on the unitaries you're applying.
Thanks.
Yeah. Did that feel like I answered your question?
Yeah, absolutely. Makes sense.
Yeah, okay, cool. Okay, so this actually, we kind of just talked about this, but I'm still going to go through it just because I feel like it really solidifies understanding. So I'm going to go through two different visible space examples, one of which is informationally complete, one of which is not. So the first one is random Pauli strings, which we were just talking about, where you apply on every single site a different single qubit Clifford unitary. And because we know that the Clifford group takes Paulis to Paulis, effectively what you're doing is measuring a different random Pauli string for this observable, which is what we were all just kind of talking about. And because of the fact that you're measuring all the different random Pauli strings in these various randomized measurements, you have a set of things that you're learning which actually turn out to be an orthonormal basis for the entire operator space, right? The Pauli strings orthogonal basis for the operator space. And so as a result, the visible space is your entire operator space. And this is what people talk about when they mention informational completeness. And just to go back to our other example, to contrast this with global SU2, where you're applying, again, the same single qubit rotation on every single site, there are a set of things that you can't learn when you have this degree of control. And as a result, you have a non-trivial invisible space. And the one thing that I want to mention is that global SU2 is actually physically motivated. So in our group, we have a neutral atom quantum simulator, which is, they use Rydberg atoms, and they can, like, sometimes at the end of their computation, translate the information in their system and make it encoded in the hypersign. And then at that point, it's really easy for them to just, like, shine a laser over their entire system and do this, like, global SU2 style measurement where every single qubit is rotated in the same way. And they can do this with very high fidelity. And so this example that we're talking about here is actually, like, very experimentally relevant. And something that's really cool is that even though the invisible space is present and is non-trivial, the visible space for this type of unitary ensemble is actually still exponential in size. So you can still, with this, like, seemingly very limited type of control, learn exponentially many things about your system, which is pretty cool. And actually, for me, when I was first doing this research, I was really surprised because this ensemble seems so limited to do the same single qubit rotation across your entire set of qubits. But yeah, but it turns out that it's exponential distance size, which is nice. Okay, so now that we've developed a little bit of intuition.
So the Clifford, sorry, like the Clifford is a subset of the SU2, right? Like.
Yeah, good. Yeah, it is.
So why, I don't know, like why is the Clifford like informationally complete and SU2 is not? You can just take a subset of SU2 and.
Global versus local. Sorry, I should have maybe. Isn't that right?
No, yeah. So for the left-hand side, you have a different unitary acting on every single site. You have like U1, U2, UN.
I see. Okay.
And so you're doing a different rotation on every single qubit. And because of the fact that Cliffords take polys to polys, you are measuring Pauli strings because you're measuring in the Z basis, right, when you're doing the measurements. And so these unitaries are conjugating Z into either X, Y, or Z. And then on the right-hand side, like Michael was saying, it's all the same unitary. That's a good question.
Thanks.
Okay. So now that we've built up some intuition about the visible space and invisible space, we are going to get into the meat, which is how we actually tailor our protocols to the learning task. And as we saw in our introduction to randomized measurements, there are two different pieces to randomized measurement protocols. The first one is actually doing the randomized measurements, and the second part is the post-processing. And when you're tailoring your randomized measurement protocol to the learning task, you can tailor both the first part, the randomized measurement part, and the post-processing. And the way that you tailor them will look slightly different. First, we're going to talk about the randomized measurement part, and then I'll get into the post-processing. So for tailoring the randomized measurements, I'm going to begin with an example because I feel like it's very illustrative. And the goal of this example is going to learn the expectation value of the all X polystring. And we have two options that I'm going to consider. The first option is what we just talked about. It's these random polystrings where you are, like we talked about before, learning a different random polystring with every single shot. And the amount of time that you learn the all X polystring is 1/3 to the n. And the reason for that is that, if you just consider a single qubit, you are either going to measure on that X, Y, or Z. And you're going to measure X 1/3 of the time. And because each qubit is going to be measured in either X, Y, or Z, you have 1/3 of the time you're going to get X on the first qubit, 1/3 of the time X on the second qubit, and so on and so forth. And so that's why you are only going to actually measure the all X polystring 1/3 to the n of the time. Alternatively, you could also consider option 2, which is similar to global SU2, but instead of applying the same thing, so if you're still applying the same single qubit rotation on every single site, but instead of sampling this unitary from SU2, you're instead sampling this unitary from the single qubit Clifford gates. And so as a result, again, because Cliffords take polys to polys, you are either measuring the all X poly string, the all Y poly string, or the all Z poly string. And as a result, you learn the all X poly string 1/3 of the time. So if we compare these two options, we have these like two different learning rates. One of them is 1/3 to the n, and the other one is 1/3. And so if you had the choice between which these two options you're going to use to actually learn your expectation value of the all X poly string, of course, you're going to choose option 2 because you're learning this all X poly string so much more often. And the point I want to make, which will be intuition that will carry on to help you understand how we actually do this mathematically, is that this global CL2 ensemble that we have on the right-hand side, this option 2, like it's actually like a subset of the random poly string, in the sense that, you know, when you're doing your random poly measurements, you will sometimes measure the all X poly string, you will sometimes measure the all Y poly string, and the same thing with all Z poly string, but you're only going to measure those some of the time. Whereas with the global CL2 ensemble, you're measuring those all the time. And so you're just restricting the measurements that you're taking to measurements that in this case are more effective at learning the all X poly string. So hopefully that helps you have a little bit of intuition, because now I'm going to be a little bit more formal. And now our goal has changed. We want. Yeah.
So in this slide, right? So, on the right hand side. So sometimes we are measuring like all X's, sometimes we are measuring all Y's, sometimes all Z's, right? So if you are interested in estimating the expectation value of all X's, do we get useful information? Right? Like if we measure just Y, then we cannot, like, of course, use that to estimate like string of X's, right? But by measuring like Y's and string of Z's, right? Is it possible to like say something about like strings of X's?
Like you're saying that if you take measurements of all X or all Y and all Z, can you learn something about the expectation value of the all X poly string? No. So actually, that you're making a really good point, which is that if you were going to be even more efficient, that instead of doing the global CL2 ensemble, you would just, if you knew that you wanted to measure the all X poly string, you would just do Hadamard on every single, like for your use, so that every single time you're measuring the all X poly string. Yeah.
So you're going to explain how, by doing this CL2, global CL2 approach, not only can you measure this all X to the n efficiently, like 1/3 of your shots, but by measuring the all Y and all Z, you can get a fairly nice set of observables as well. Like it's worth doing this over just the straight.
This is interesting. So as you might expect, the visible space for this ensemble is any poly string that has, for example, only X's in it, only Y's in it, or only Z's in it. So you might have, like, so any string that also has identity, right? So like identities of X, identities of Y.
Like a shorter version,
and so
a string that's like half the system.
A shorter version, exactly. Exactly. And so it's not just the all X, all Y, and all Z poly string. And so if the things that you're interested in learning are just in this set of poly strings or in their span, then you're good to go with this.
I see.
Ensemble. But if you're trying to learn things that are outside of it, then obviously you're going to need to make some different choices.
Are you also going to talk about like how to estimate nonlinear observables?
So I am going to generalize what I'm talking about here and not restrict to poly strings anymore. And I won't be talking about anything like purity, but you could have, like, the same sort of thing applies in those cases, in the sense that if you have but you can still construct nonlinear functions of your state, and these protocols will also work, and the visible space will give you a sense of what things you can learn. Like for example, let's just be very concrete here for a sec and give you an example. So if you want to learn the purity, right?
Yes.
Like what purity is it's traced row O, or sorry, it's traced of row squared. And like another way to say that is that it's also trace of row tensor row with the swap operator.
Right.
Right. And the swap operator actually, when you break it down, is a sum over the polystrings tensored together. And so you need the entire visible space to be able to reconstruct the purity. Let me say that again.
Yeah, that makes sense. Yeah.
Yeah. And so, like, if you have only like a visible space that is not the entire operator space, then you won't be able to reconstruct the purity. Or you'll only be able to reconstruct the purity in a certain portion of the operator space.
Right. But
Yeah.
but it would be more efficient to like estimate purity by doing something like a global Clifford rotation, right? Like rather than doing these like single qubit like Cliffords, if you do some like global unitary, that would make it easier to estimate things like purity.
Intuitively, that makes sense to me. I've actually never seen a derivation for that, so I don't want to say something that
It's also my intuition.
concretely. Okay, great.
I've
but I
heard like
think that's
people
something.
say, yeah, I've heard like people tell me this, like multiple people tell me this, so I kind of like accepted that it's like a well-known fact, but I've never seen it.
I wouldn't be surprised if someone had worked on it. So when Robert put out his original like classical shadows nature physics paper, one of the things that they didn't do that he posed as an open question for someone to solve was to actually compute the sample complexity for learning these nonlinear functions of your state. And obviously then when you compute the sample complexity for that, then you can evaluate whether or not it's like, applying a Clifford circuit across your entire system versus like a random polystring style approach would be better. Okay, so let's formalize what we've been talking about so far with tailoring the randomized measurements. The goal here is to, like we talked about before when we were formalizing in the first part of the talk, is to learn some set of observables. And because we are working with this definition of the invisible space and the visible space, we can only learn the expectation values of these observables if they all live in the visible space. And we also talked earlier about this idea of, when you have this visible space, you can learn any property that lives inside of it. And so in this case, if you're only interested in learning the expectation values of these observables, then you don't really care about the part of the visible space that you have access to that is outside of this circle, right? Because you're not interested in those observables, and it's being sort of wasteful to use your measurements to learn these other portions of the visible space that you don't ultimately care about. So really what you want to do is you want to restrict your visible space such that it only includes the operators that you are interested in. And the way that we actually do this is by defining a probability density function over the set of unitaries that we are sampling from. In all of the previous randomized measurement protocols, what they do is they just uniformly sample from this set of unitaries. But of course, that is giving you access to the entire visible space, but that's not going to necessarily be most efficient, like we just talked about. And instead, what you could do is you could update this uniform probability density function and make a new one that only samples unitaries with high probability if those unitaries are helpful at learning the observables that you're interested in. And so just to say that in another way so that it really lands, is that if you say that there is some unitary that is really good at learning some portion of the visible space, but that portion of the visible space is outside of this yellow circle that has the observables of interest, then we never want to use it in our randomized measurements because it's not ultimately going to help us. So we want to make sure that when we're actually doing our randomized measurements, the probability of sampling this unhelpful unitary is set to 0. And we show in the paper, like mathematically, how to actually update this function. It's not that hard to do. I refer you to my appendices, or we can also talk about it after if you're interested. Okay. So
I have a question, Catherine. Sorry. So this, so I mean, if we wanted to go back to this, in this, hopefully I'm not getting this wrong, but if we wanted to go back to the simple example of this, the way that we would tailor, like if we had the global set of Clifford gates, then we could tailor ours by making the probability that either a all y or all z measurement would be 0. Is that how you would tailor it? So that if you wanted to all exactly. X, that would be the tailoring. So then, in a sense, though, right. In a sense, though, how necessary is keeping some of it randomized? Because the other thing that you said was that you could just make them all Hadamard gates. So in essence, if we did something like that, we would be making them all Hadamards and losing the random feature. So in a sense of, I guess, a more complex system, how important is having some randomness in the left in the V's?
You want your circuit?
Go for it.
What's that, remember?
I was just saying, like, you cannot make different circuits for each different case, right? There has to be some generalizable features. So there's parameters that you can tune to. Like, I don't know if that answers Rick's question.
So, and can I add a couple more things onto that? So the first thing I would say is that in this case that we considered, let me just go back to it. Great. Okay. So in this global CL2 case that we were talking about that Eric just mentioned, if you update such that you are every single time learning the all X polystring and you're not learning Y or Z, then you're just sampling the Cliffords that when it conjugates to Z, it takes you to X. And when you do those, the only difference is a phase. Mm-hmm. And so ultimately actually when whether you just do all Hadamard versus the Cliffords that take Z to X, and that full set of them, it actually doesn't matter.
Sure.
And then in the case where you have this, so obviously when you look at this all X example, it's super obvious what to do, mm-hmm. because it's just an X example. As soon as we can see this really well and understand what to do. But in the case where you have a set of M different potentially really complicated observables, it's not necessarily clear when you have a very big set of unitaries that you can do on your quantum system what the best way to update the probability density function is. And so the way that we went about doing this is that we actually formulate a measure for we quantify how helpful the unitaries are for learning this set, the full set of O1 through OM.
Okay. And
then we update the probability density function with this sort of quantification of helpfulness.
Oh, okay. So I see. So the example it doesn't necessarily show how randomness plays a role in this final result. I see. But exactly. That makes a lot of sense. Okay, thank you.
Yeah. No, thank you for the question. I think that's a really good point.
So this is a kind of classical pre-processing? Is that a way of putting it?
Yeah, so basically, if you know ahead of time the observables you want to learn, then you can be more effective at choosing the probability by which you choose your unitary.
Uh-huh.
Yeah. Which is nice.
Yeah.
Okay, so let's talk about tailoring the post-processing. So of course, in like this most general formalism, you want to learn some set of observables, but what I'm going to talk about here is I'm just going to consider one to just make things simple. And you can do this technique of tailoring the post-processing for all of your observables. And the way that we tailor the post-processing is by biasing the observable. And at least like when a lot of people first see this, it feels a little bit weird. So I'm just going to go through this slowly. So first, this observable that we're interested in learning, of course, because we're trying to learn it, it must be somewhere in the visible space. And we want to find some observable, which is O tilde, which is really, really close to O. It's somewhere in the vicinity of O. And so as a result, the structure of O tilde is very, very similar. And another way to say that is that by learning O tilde, you're effectively learning O because of the fact that they are so close together and they're so similar. However, the key difference is that the way in which these two observables are not the same, like the way in which they're different, allows you to learn O tilde with many fewer measurements. And the difference between the two is actually called like the bias. And so that's what I mean when I say that we want to efficiently learn the expectation value of O by biasing O into this new observable O tilde that is very close to it, but requires fewer measurements. And so you can imagine here, but Katherine, if we're interested in learning O, why are we learning O tilde, right? Doesn't that seem a little bit weird? And what I would say is that there's sort of there's a trade-off and there's a cost, right? If you learn O tilde instead of O, you're not being super exact, which, gives you a cost in your estimation error, it introduces an error. But on the other hand, you require, in some cases, you require many, many fewer measurements. And as a result, you don't really mind that there is a slight difference between your two observables because you have so many fewer measurements that you need to take. And this might be a little bit of a weird concept. It's actually a very common concept in learning theory. It's called the bias variance trade-off. And what I'm going to do now is I'm going to go through a very, very simple toy example of how the bias variance trade-off works. And then I'm going to come back and I'm going to re-explain this in a little bit more detail. Okay. And hopefully this will make a little bit more sense.
So just to be clear, so the O is one of your OMs in the previous slide?
Exactly.
Okay, so exactly. it's one of our, we've decided originally we like these O1 through OM observables.
Yeah.
And O tilde is an observable we might like to learn, but it's not in the, it's not a high priority or something like that?
So if, let's say that, let's just choose O1. You can do this for all of your O1, O2, and everything through OM. And so if we just take O1, instead of learning trace row O1, we're going to instead learn trace row O twiddle 1.
Oh, okay.
And so we're replacing O1 with O twiddle, or in this case, I just called it O. We're replacing O with O twiddle. And because O and O twiddle are so close together, they're basically the same thing, by learning O twiddle, you're effectively learning O.
Okay.
But the nice thing about O twiddle is that you require many fewer measurements.
I see. Yeah. So O tilde could be very efficiently produced. But it's not quite the optimal thing you wanted to produce to begin with, but it can be produced.
Exactly.
Okay, good.
Yeah. Okay, so the toy example is as follows. Let's say that you have a set of data points and you want to fit a line to this set of data points. Here's an example. As humans, we can look at this and we any of us could draw a line through this. And imagine that we're fitting a line to this. But if you wanted to be really, really precise and exact, you might imagine drawing a line such that you go through every single one of these data points. And this would be a very high variance estimate for this task. And again though, what's nice about it is that it's very precise. The line goes through all of these data points. But if you look locally, there are lots of little local fluctuations in the line, right? There are all these little jagged pieces. And so you might say, okay, I actually want to be insensitive to these local fluctuations. But you could imagine that if you're so insensitive to these fluctuations that you come up with a line that is doesn't capture the underlying structure of your curve. And so what you really want is you want to sort of interpolate between these two different regimes and find this best fit. And so these two regimes are this like high variance regime or this high bias regime. And so you want to slowly increase the bias and decrease the variance, but only to get to this regime where you have this best fit. And this analogy, like while it like seems like incredibly simple and like funny to talk about in a talk, it's actually really nice because it directly relates to what we're doing in the randomized measurement tailoring case. So let's just like literally like make a side-by-side comparison to understand this. So our task here, instead of fitting a line to a set of data points, is to efficiently learn the expectation value of some observable. And like we talked about before, our observable lives somewhere in the visible space. And this observable, you could consider like the high variance case. And like what I mean by that is that you are being very exact, right? Like if you want to learn O and you just learn it, then like you're doing it exactly, right? Like in the same way that this line goes through all the different data points, and it like goes through it exactly. But on the other hand, you could imagine that you very highly bias your observable, and you find some other point in the visible space that you learn instead. But the problem might be that this observable that you are considering instead, this yellow one, is really, really far away from your original observable, and so it like doesn't capture the underlying structure of your original O. In the same way that this like kind of straight yellow line on the left-hand side didn't really capture the underlying structure of the curve. And so instead, what you want to do is you want to find some optimal observable, which we call O twiddle, which interpolates between these two regimes where it's really, really close to the original observable. So it captures the features of that observable. So learning O twiddle is still effectively learning O, but it requires many fewer measurements. And I'll just make a few remarks on how we actually do this, but I won't bore you with the math. But basically, like you can write down a cost function where one term is the variance and one term is the bias, and it's a convex function. And so you can just literally do a sort of like gradient descent to find the minimum and get your optimal O tilde.
So maybe I can try to restate it from what I understand. So
Yeah.
You want to measure O, but what you're saying is you could measure O tilde and somehow more efficiently measure O? Is that what you're saying?
Yeah.
So
exactly.
Because I would have thought you could measure O tilde very efficiently because it's somehow more optimal. But
Yes.
then to measure O, you might need to take a little more samples than you did to measure O tilde, but still it's more efficient than directly measuring O. Is that?
Yeah. So if you're interested in just learning O tilde, then and that requires fewer samples, then it's like great. But if O and O tilde are very, very close, like let's say you like take the difference between these two operators, and there's like a 0.0001 difference. You know, like if you like take the difference and then you like maximize over space, then and then you take the trace. And you get this like very, very small number. But, and this actually happens, like you'll take the difference between these two operators that are effectively very close, and you'll get this like tiny, tiny number for their difference. But then this O tilde that you're working with will actually require many, many fewer measurements. And so like in practice, basically, because of the fact that you're learning O tilde instead of O, you have some like 0.001 error that gets introduced into your estimation error. But you don't really care because that error is so small.
I see.
I guess I guess my question with the bias variance trade-off is, how easy is it to locate O tilde in the space of O's between high variance and high bias? Like because
that's a great question. Yeah. So two statements. So one, it's a convex function, so you can always learn the minimum. But two, it will be as your system size gets bigger and bigger, and if you have some like really complicated ensemble, right? Like if you have in a given experimental platform that has some like weird set of unitaries that you're applying, then finding that can actually be kind of hard. And so you aren't necessarily going to find the optimal, but you can still find one that's really close to it, or at least one that's better than the one that you started with. But in cases where you have very small system sizes, then you can just find the optimal one and you're good to go.
So maybe we should think of your initial data that you said you want to measure O1 through OM. But you should add to those observables, to what accuracy do you want to know O1 through OM? So you have now two sets of things. And then within that accuracy, now this can make you're taking advantage of that to make an even more efficient algorithm.
Exactly, yeah. Okay, so hopefully we have a grasp on what we've talked about so far in the algorithm that we proposed. And so now I'm just going to very quickly show you an application of how these actually work in practice. The task that I'm going to consider is estimating the energy density of the U1 lattice gauge theory. And I'll just start by introducing the lattice. So here we have a triangular lattice that extends in two spatial dimensions, and we have periodic boundary conditions, which you can see by the fact that you connect the solid lines and you connect the dashed lines. And for each of these spatial plaquettes, we actually have them extending in another dimension. And on all of the edges of these sub-plaquette triangles, you have qubits. And here the qubit is denoted by a gray dot. This lattice and the associated Hamiltonian, which you see here, was proposed by the reference at the bottom of the screen, which just showed how to efficiently simulate this theory on a quantum simulator with qubits. This Hamiltonian at first looks a little complicated, but I just want to pick out literally two things about it which are important for our task. So one, we're estimating the energy density, which means that we just want to learn these terms, which I've circled in red and blue, in order to learn that energy density. And these terms are both very local. So this red term that I circled, this triangle, it connects the qubits and makes them correlated that live on one of the triangles in the stack. And then this blue term is what I call sort of a link term, because it links two qubits that are adjacent in stacked triangles, as you can see in the figure. And even though what I've shown you here is just one example of H triangle and H link, these terms extend all across the lattice and all up and down this stacking that you see here. So with this framing, we can now apply our techniques. And the first thing that we can see is that the terms of this Hamiltonian live in the global SU2 visible space. Remember that global SU2 is this ensemble that we talked about where you're rotating via a SU2 unitary, and that unitary is being applied to every single qubit. And so that's really nice. We can use this limited form of control to learn the terms in this Hamiltonian. The next thing that we can do is we can tailor the randomized measurements to the observables of interest. And if you recall, what that means is that you figure out where in the visible space your terms of interest are located, and then you update this probability density function so that you're always learning the observables in the region that you're interested in. And then finally, we can also tailor the post-processing. And recall what we did is we talked about this bias variance trade-off, and we can, for these two terms in your types of terms in your Hamiltonian, you can bias them and come up with H triangle twiddle and H length twiddle. So when we actually apply our technique, this is what we get. So this top line is just using global SU2 to estimate the energy density. And what we're showing here is the number of measurements as a function of system size. And this gray line uses none of our algorithms or techniques. For the pink line, we're still using global SU2 to learn the energy density, but we also are tailoring the randomized measurements in this step. Next, for the blue line, we're still using global SU2, but we tailor the post-processing to the observables we're interested in. And then finally, for the purple line, we tailor both the randomized measurements and the post-processing. And what I just want to point out here is that for a system size of 225 qubits, you only need on the order of a couple hundred measurements in order to learn all the terms in this Hamiltonian up to epsilon of 0.01, which is really, really good. and really striking. So it really demonstrates that what we're doing here with the Taylor array works and can, in practice, really reduce the overhead and the resources required to learn whatever it is that you're interested in.
Yeah. So, do you have any idea how big was your the unitary group that you were like in this case where you tailored the randomized measurement?
So we're using global SU2 in this case, which is the unitary ensemble where you apply the same single qubit rotation on every single site, and that unitary is sampled from SU2.
Okay. Oh, I guess I meant to say that for the post-processing, like where you okay.
Yeah, I think what Maber was saying is, doesn't it shrink basically the set of unitaries
like how
you
much
use?
it shrinks? Yeah.
Or you just lower the probability of some of them so that they're still there, but it's very unlikely that you choose them.
Oh, like when you're tailoring the randomized measurement.
Yeah.
Like when you're updating your ensemble. Yeah. So.
I think he might, maybe another way of asking Maber's question is, you've got two things you want to know only, maybe. So maybe that's, oh no, it's actually a lot, actually, right? Because there's a whole set of each site has a different, there's a lot of observables.
Yeah.
So the way that I understood it was that, like, the way I understood it is that the size doesn't change, but the probabilities of those, like the tailoring doesn't necessarily change the size of the group, the global SU2. Instead, what happens is the probabilities of getting some of the outliers shrink. So like the things, right. So it's not necessarily the size gets smaller, but the probability is getting the things unwanted shrinks. So there's, as you get closer and closer to the, it's more like instead of like a hard cutoff to the outside and you just have that, it's more like Gaussian is how I understood it.
Yeah.
So my question was, how, you know, with the tilde operators, how far from the exact values are you getting? Do you have an estimated error for how the bias variance works? So that, like, because I imagine if you did like imagine there's a way to do this where you just get the exact, H tildes and H operators, and then there's a way to get the H tildes. Like, how big is the error for that bias variance? Do you have a?
Yeah, so I actually have a slide on that. I don't want to give you guys whiplash, but I'm gonna flip, so just be ready. Okay, so if you look on the right-hand side, this second plot that you now see is the estimation error as a function of becoming more and more biased. And then the different colors on this plot just represent the estimation error corresponding to a different number of measurements.
Wow, no, that's pretty remarkable there. That is very, very small.
Yeah. And isn't it, it's shocking, right? Like, it's a tiny, tiny bias, but it can make such a big difference. And also another thing that's really nice is this wide plateau, right? Like we talked about for large system sizes, that you can't always necessarily find like the exact minimum. But if you have a really large plateau like this, as long as you get something that's like at least better, you can do actually quite well.
Why does the error go up for small bias?
Same question.
Yeah. So remember how we talked about this sort of, like, we were interpolating between these two regimes. There was the high variance regime and the high bias regime. So as the estimation error, it has a variance term and a bias term. And so as you get towards these two extremes, like the variance is going to really, really, really dramatically increase. That's happening on the left-hand side of the plot, right? Like as you get to like very small bias, you like your estimation error gets a lot bigger because the variance is really high. But then as you go to the right side of the plot, you are getting more and more bias, and you're observable that you are, like, your O twiddle no longer looks like your O. And so the bias, i.e. like the difference between these two, becomes a lot bigger. And so the estimation error starts going up because, of course, the estimation error is going to depend on how good your O twiddle is compared to O, right? Like how close these two things are. And if they're really far apart, then O twiddle is no longer going to be a good estimator.
So in the small bias, it's more of just like a a feature of the program, where like at the high variance your bias goes up for some reason, but it's not like it's not necessarily that there's a large estimation error there because you're getting like right up to the variance level. Is that right? Maybe like, or maybe one way you could say is the difference between the left side of this and the right side of this is that the right side can still be produced with minimal measurements because you have like because you're still in the land of O tilde, you're just in that very biased land. And then the one on the left, you're getting closer and closer to O, so that the variance goes way up, and then the estimation error could be like switching to like how long it takes to calculate it because of how many more measurements and whatnot.
Exactly.
Okay.
Great. Yeah. That's awesome. Yeah. Thank you guys for being so thoughtful. Okay, so I'll go back. And I just wanted to mention a few things and give you a few takeaways and mention some future directions. So, like, as we saw today, it's really useful. And what we've done in this work is we've shown that you can, like, if you have some set of experimental controls, you can figure out what you can learn given those controls. And we've defined this with the visible space, which is really, really nice, especially for experimental platforms in the near term. Next, we've also showed that you can tailor both the randomized measurements and the post-processing to the learning task. And then finally, we showed that when you actually apply these protocols, you can get a dramatic reduction in the number of measurements needed. And again, like going back to the start of this, like the name of the game for these protocols is how do we learn what we want to learn as efficiently as possible. And what we're doing here is we're making every step of the process as efficient as it can possibly be. Along those same lines, we have some future directions that could potentially also make this more efficient. So one is adaptivity in your randomized measurements. We talked nothing about the state that you're working with, but you could imagine that after 10 measurements, you know like a little bit about where your state is in the Hilbert space. After 100, you know a little bit more, and so on and so forth. And so if you slowly, adapt your probability distribution as you learn more about where your state sits, you could also be more effective with your measurements. You could also use, for example, if you know that the state you're creating in your quantum simulator has an efficient tensor network representation, then of course, you could also use that underlying assumption to update the number of measurements that you need. And then finally, you could also imagine recasting all of this stuff in the language of bosonic and fermionic degrees of freedom. I think it was in November, there were some really interesting classical shadows works that took us into these regimes. So with that, I just want to say thank you and acknowledge my amazing collaborators, Nisha, Jordan, and Robert. Thank you.
All right. Thank you.
Thank you. Very good talk.
Thank you so much.
Any questions? Any final questions?
We're already 10 minutes over, so
Yeah, we're already a little
I'm
late.
good. I thought it was a very well-rounded talk. I like all that.
So,
So I have a question.
Thank you.
So earlier we were talking about like swap gate in terms of measuring the purity. So I'm trying to think like what would like trying to figure out like ways of like measuring the purity more efficient, because like right now the methods that we have for measuring purity are really inefficient.
Yeah.
So is there a of carrying out this like bias versus like variance trade-off in measuring the purity? Like what would be like O for us would be like the swap gate, so what would be like O tilde?
that was all linear observables, I imagine, isn't it? That the way you were thinking of it.
Yeah, so I posted it for linear observables, but it could potentially be extended, I think is what you're getting at.
I actually know the swap one. It's like you can because that's what Michael and I do. You can actually have this like variance in your swap where like you can't swap all of the information from one qubit to another, so you only swap part of it, and then you can adjust your parameters to get like a stronger swap gate. So like there's ways of thinking about it with the swap function where you have extra parameters that control how like efficiently the swap happens that you could kind of maybe control with a bias variance method like you did. But
Yeah,
as far as purity goes, that's a completely different monster. That's a lot harder. Because swap,
the purity,
yeah. Sorry, go ahead.
The purity is just this, like, it's the trace of row tensor row with the swap operator.
Mm-hmm.
So
Brian,
I guess, like, for
maybe I'm thinking about it in a very, I'm probably thinking of it in probably too much of a specific use case than something that could be applied generally to like swap operators and maybe not. I don't know. I'd have to think about it more. I guess maybe I was thinking too specifically when I thought of.
So the swap idea is you double the number of your states. So you have two copies of the state at the same time, and then it becomes a linear observable again to get the purity. But that's that's at doubling the number of qubits. So maybe there's another way that doesn't require that. I don't know.
Right, like if you do a tomography, if you do like randomized measurements, it's like having like infinitely many copies of the system. So like once you enter this like regime of like randomized measurements, then like having 2 copies of the system to measure the swap gate is not actually like necessary.
I mean, it's still, if you have a 200 qubit computer and you want to study a state that is 200 qubits, right? You cannot study the two, you cannot make 2 copies at the same time. You can.
Which is
right.
one of the reasons why people like randomized measurements for this task. Because for large system sizes, you can't create 2 copies.
You can't do that.
Yeah, but you can still use randomized measurements to reconstruct an estimate for the purity, even if you don't, of course, have these 2 copies. And it's not clear to me, like if you say that you did bias the swap operator, just for the case where you're using randomized measurements to learn the purity, it's not clear to me like what the like ideal bias swap operator would look like. What I would do if I was doing that.
Yeah, because like in so if you're thinking about like quadratic operators, right, like quadratic in row operators, then the simplest operator is the identity, right, like which is the purity. Purity is like trace of identity times row squared, right? So I can't think of a way to like bias this quadratic operator in a way that would make it more efficient because it's already the simplest quadratic operator that you can think of.
Oh, I see what you're saying. The way that I would think about it, if I were, say, to do the bias variance trade-off for learning the purity, is I would bring us into the case where you have like row tensor row and you're learning the swap operator.
Yeah.
Like I would think like
that's a simple translation of everything you've told us today. If you did that way.
Yeah.
Yeah.
Yeah. Yeah. But I mean, maybe that's not like the best thing to do. And honestly, I mean, in our paper, we don't formalize anything for nonlinear functions of row. And so I actually think that would be a really cool thing to look into.
Does sound cool to me.
Yeah.
I think that do because like especially these days because like people in like condensed matter physics are now starting to think not just in terms of like correlation functions and linear observable. They're like interested in like the entanglement dynamics. So if we have like some like better ways of like studying like things like purity and entanglement, that would be great. Like that would be great progress.
People would be really, really interested. I mean, especially like getting the entanglement entropy more efficiently actually is something that I thought about for a really long time in the start of my PhD, because like experimentally, it would be really cool to probe the topological entanglement entropy. So, I mean, if that could be done, that would be great.
Yeah, this is also something that I've been.
If you have ideas, come talk to me. What did you say?
Hey, I'm sorry to interrupt, but I have to go.
You gotta go. Yep.
Catherine.
All right.
That was a great talk.
Yeah, it's nice to meet you.
Nice to meet you
See
too.
you, Eric.
Take care, everybody. I'll see you.
Yeah, so there is a seminar running at this moment. I don't know. It's kind of.
Yes.
We could call this. We could call this to a close, and we can keep chatting in the future. How does that sound?
That sounds great. It was so nice to meet you guys, and thank you again for inviting me to give a talk.
All right.
Thank you, Katherine.
Yeah.
Great.
Bye.
Thank you. Bye.
If you don't have to go immediately, I have some more questions. If you have some time.
Yeah, do you want to just email me?
Oh no, like, do you have to go right now, or can we stay longer?